are taught to make certain patterns with characters in some beginners C programming class or so, right? So we used to draw the waveforms in that manner. So in the last 15 years or so, this electronic design tool development has seen a radical shift, radical transformation from a CUI based tool to a GUI based tool which we use nowadays. And the other thing which we should keep in mind is that the circuits are quite big. We shouldn't spend a lot of time to go on designing again and again the same thing. We should find out ways by which we can reuse the existing resources in the design. That is again something which the object oriented programmers frequently do. They use the notion of reusability of certain classes for their designs. So once you create a class, you can use it for creating any number of objects you like. So the similar thing is typically used by the VLSI designers. Once they make a block, they put it in the library, and you can browse the design from the library and copy it at any number of places you like in your design. So we feel that we should be happy by just borrowing our notions from some book like Pressman or so, and develop some CAD tool with those philosophy or like that. But there's a big but to it. The hardware is concurrent. So if you have two hardware modules connected to the same input, the two modules will run concurrently when any change in inputs occur. If you take the analogy with some process, software process, the set of codes within the process runs sequentially. So we have to find out ways by which we can introduce this notion of concurrent execution of separate modules when it comes to a hardware modeling. So one of the big problem is that when we are modeling the hardware, we are writing a set of code that will again execute in a uniprocessor architecture. So when we are actually running the tools, the codes are actually running sequentially, but we have to engineer the display of execution in such a way that the person sitting in front of the screen who is actually analyzing the circuit with the help of the CAD tool will see the things running concurrently. And this is one of the important things that you should keep in your mind when you are going to design a CAD tool for modeling a digital hardware. So the other thing is that hardware behavior has timing as an integral part. So you have to establish timing relationship between the different components of your system. That is not the case with the software. So with these constraints in our mind, we define a hardware language, description language, as one that has got the ability to describe and simulate at the various levels like structural, behavioral, a mixture of structural and behavioral or so, and then synthesize a circuit from it. So the problem is even more intricate in the sense that given a description of the circuit in terms of its behavior, you are actually synthesizing or generating the circuit. So all these power has to be incorporated into a typical hardware description language. So two approaches are typically followed when we develop systems. One is the top-down approach, in which you start with the system as a whole and go on splitting the system into subsystems, sub-subsystems and so on, ultimately arriving at the elementary level systems which you can manageably handle. The other approach is the bottom-up approach that starts with the elementary level components like the transistor level or gate level components, and you go on adding components incrementally to it, ultimately arriving at the whole system. So if you see the philosophy of the top down approach, we start with the top level block, then split it into certain sub blocks and ultimately arriving at the leaf level blocks. I mean, I have shown it in 3 levels. That doesn't mean that it should have a 3 level splitting or so. It can split this level of this splitting of sub blocks into further sub blocks can go on iteratively. Ultimately, that can lead you to the leaf cells. So should we go for the top down approach or should we go for the bottom up approach? Obviously, we can see that top down approach, since it leads to splitting the it leads to visualizing the system at the beginning from an algorithmic perspective, and then goes on splitting and resplitting the system, ultimately arriving at the elementary level systems, then top down approach should obviously lead to a fast design process. But again, when you are designing it fast, if you just think it from the common sense perspective, when you try to do a thing at a fast rate, you may lose doing certain things. Enhanced speed in the design process can lead to sacrifice in terms of the accuracy. So the bottom up system is typically used in cases where we are very much particular about the accuracy of the system. So typically in digital design processes, we use the top down approach, where we are not so much bothered about noises and disturbances, because the digital circuits are designed in a manner so that a range of voltages correspond to logic 0 and a range of voltages correspond to logic 1. So accuracy is not that much needed, although it is not really true in the perspective of 2011, because now the VDD has come down to as low as 0.6 volts, and the so that means you have only a range of 0.3 volts or 300 millivolts for logic 0 and 300 millivolts for logic 1 or so. So again, people are rethinking that whether they should use bottom up design in digital systems design or so. And the recent trend is that you use a combination of both the top down and bottom up approaches. So you use the bottom up approach up to a certain point and then go in the other direction, that is start splitting the system using the top down approach and reach to that point, and then interconnect those designs to get the design for the whole. So in essence, we use a mixture of top down and bottom up approaches for designing the circuit. So if you see the top down way of analyzing a 4-bit ripple carry adder, you can visualize the 4-bit ripple carry adder as a collection of 4 single bit full adders, and each full adder comprises of XOR, AND and OR gates. So you ultimately arrive at the level of XOR and OR gates, design the XOR and OR gates, and then integrate them into the single bit full adder and integrate the single bit full adders into the design of the 4-bit triple carry adder. So looking at, so if you go by the top down approach, at the initial stage you have to have a algorithmic way of analyzing the system. So in a typical design process, at the very initial stage, our idea about the system is very unclear, hazy and abstract. We know that what the system is going to do, we don't know what the system is going to be built of. And therefore, we start with an algorithmic design of the system. So we start with a formal description of the system in some hardware description language. And once you formalize your specifications about the system, you use a simulation engine to detect whether there is any error or flaw in the specification or not. Once you are confident enough about your design, you use a synthesis tool or a synthesizer to generate an equivalent logic netlist. So sequential state machines, you go on visualizing the system as a collection of some states and go on splitting and further splitting the states, ultimately arriving at the elementary level states which you can easily implement in circuit. The other thing which has become very common recently in the design of systems is the hardware software co-design. Typically now when we want to bring out a product, the time frame within which we have to bring out our product is very limited, and therefore we have to figure out that in order to speed up the design processes, what are the things we shall implement in hardware, what are the things we shall implement in software, and then we can have the software talking to the hardware to get the task accomplished. So lots of optimizations take place when we do this hardware software co-design. While in case of hardware, we gain a lot in terms of speed of execution of the system, because hardware execution essentially means some circuits functioning, so you don't really need to go for writing an algorithm that will comprise of a set of instructions which you go on fetching, decoding and executing, and you do on the iterations to accomplish the particular task. On the other hand, software will give you a lot of flexibility. So there is a optimization of accuracy and speed versus flexibility when you go for this hardware software co-design process, and that has become the key driving force behind the development of embedded systems in today's scenario. In fact, in the last on Friday and Saturday, I was at IISc. We have an embedded systems consortium, All India Embedded Systems Consortium, in which some of us are associated with it, and we were in fact discussing that embedded systems has become so important that it has invaded our everyday's life. We knowingly or unknowingly use embedded systems. The mobile phone which we use, which every fruit seller or even someday we will find that some beggar is begging for alms with a mobile phone in his hand. Yeah, in fact, I will not feel shy to tell before all of you that even before I took a mobile phone, I found fruit sellers using the mobile phone in the market, and when I actually felt it necessary, I only took up the mobile phone. That was when I was in the BTech 4th year. So even before I took it, I saw some guava seller and apple seller. They were taking out mobile phone out of their shirts and talking to some persons. So embedded systems has invaded our lives, and we were discussing whether we should have a course like embedded systems for all, which can be taught just like electrical engineering or mechanical engineering basics we teach in the first year. So we can teach embedded systems to civil, mechanical, electrical, and students across all streams, and we are in a process of designing a curriculum for that. The last thing about this is the formal verification of the system. Formal verification is a hot topic of research interest nowadays. You have to develop certain formal methods by which you can exhaustively verify the different components of your circuit. It is different from the timing verification or design verification. We can verify the behavior of the circuit even at its very design inception phase. So the algorithmic description or the procedural description of the system has to be translated into some structural or logic design. So you transform the process or behavior of the system into some interconnection of logic gates or modules. How we can do this? We can synthesize a netlist from the behavioral description of the system and then use a simulator to detect the presence of errors in the design. So for that we do the popular fault simulation, and in fact we also incorporate certain components in the circuit called for built-in self-test components. So they generate various test patterns to exhaustively test the various logic in the circuit. Now after the gate level design, we come to the transistor level design, where we design the circuit as an interconnection of various transistor level components. And at the transistor level, we exercise the switching capabilities of the circuit. We see whether the timing behavior is met or not, and then we also model the circuit in terms of nonlinear differential equations that depict the behavior of the various components in the circuit. So up to the gate level we can play with the Boolean equations, but when it comes down to the transistor level, we have to start playing with the physics, real physics of the circuit. So, and when we are really talking of 30 nanometer, 40 nanometer technologies, the design of circuit is no longer mathematical. It has become, mathematics will fail to answer beyond a certain level. You have to have in you lots of depth in physics to handle all those issues. So knowledge in physics is necessary to design circuits, whatever the circuit is going to be in today's scenario. So after the circuit design phase comes the layout design phase, in which you go through all these steps. So you first partition the circuits into components and subcomponents. Ultimately you arrive at the components of manageable size, which is basically this partitioning phase. And after that you define the places on your chip where you are going to place the different components. That is basically the task of the floor planning and placement phase. And then you define the interconnections amongst the different components in the routing phase, which again spans over two subphases like the global routing and the detailed routing. So in the global routing phase you define the approximate pathways of the interconnects, and in the detailed routing phase you exactly define the pathways of the interconnects. And then you use Design rule checkers or DRC is for checking the mask geometries, and circuit extractors are used for extracting the final circuit from the mask layout, with the help of which you do the layout versus schematic verification. Almost in all the CAD tools that comes up nowadays, you have got the facility to do the layout versus schematic verification to see whether the post layout simulation results agree within a certain limit with the schematic simulation results or not.